Hi, my name is Talia from the University of Washington, and today I'm going to talk about ornaments for proof reuse in Kak. So this is work that I did with Nate Yazdani, who's here, and Dan Grossman, and also John Leo. So I'm coming from the Kak community, and in theory, we really like dependent types, because they let us do a lot of cool things. To see some of the benefits of using dependent types, let's consider sort of the hello world example of dependently typed programming, a length indexed vector. So a vector is exactly a list, except that it's indexed by its length. And this means a lot of things. So it means, for example, that whereas we'd have to write this length function over lists, it'd be pretty silly to write the same thing over vectors, because in order to have a vector as an argument, we already have to have its length. So this is one benefit of dependent types. They give us some functions for free. Now another benefit of dependent types is that they let us enforce invariants inside of functions. So to see this benefit, let's take a look at this zip function from this HS to Kak library. And I'm going to use this as an example throughout my talk, so I want to make sure we understand this. So I'll walk through how this function works, and then I'll show you what we can get if we port this function to use vectors instead. So zip takes a list of A's and a list of B's and returns a list of pairs A times B. Now if either list is empty, it just returns the empty list. And then in the cons case, it puts the first two elements into a pair and then conses that on to the result of zipping the tails together. Every zip function that does something like this has to make some decision about how to handle lists of different lengths. And the decision that this particular function makes is to truncate off the end of the list that's longer. So in other words, this zip min invariant holds the length of the result of calling zip is the minimum of the lengths of the inputs. As a consequence of this, another invariant holds if we restrict ourselves just to lengths of the same length. In particular, the length of the output of calling zip on these two lists is the same as the lengths of the inputs. Over lists, if we'd like, we can prove these invariants, but what vectors let us do is actually enforce these in a nice way inside of the type of the function itself. So we can, enforce the zip min invariant in the zip vmin function, and then the person who is calling this function will know that the result has the minimum lengths of the inputs. Or we can enforce this zip length invariant inside of zip v, and the result of this is that the user can't even call this with lengths of different or with vectors of different lengths. We don't even have to worry about these cases. These are some reasons why, in theory, we really like these things. But unfortunately, in practice, things don't always look so nice. Some quotes from experts on Kak Club on length index vectors include not suitable for extended use, and almost no one should be using them for anything. To understand what can be hard about these, let's take a look at what happened when I actually tried to write the zipv function by hand. The first time I tried, I got this scary looking error. And the reason it was kind of hard is because I realized I was really trying to do three different things at once. First, I had to write the zip function. Then, I had to thread these lengths all throughout my function, carry this index around everywhere. And then I had to actually prove that this invariant holds. And I had to pass this proof all throughout my function. In other words, programming with dependent types really amounts to doing three things at once. And once you look at not only writing functions, but also proving how they relate to each other, there's even an additional step, which I'll talk about towards the end of the talk. And if this is just the hello world example, imagine what this looks like when you use more complicated types than this. So this is where our work comes in. We've written this tool called Devoid, which makes this whole process of programming and proving with dependent types a lot easier for a certain class of dependent types. And it does this by reusing functions and proofs that the user writes over unindexed types like lists. And from that, it can derive functions and proofs over vectors, taking care of a lot of the plumbing automatically. So effectively, programming with devoid amounts to doing just two easy things: writing these functions and proving these invariants all over the on-index type. And this is work in progress, and I'll talk about this later, but I think that for the class of types that we handle, even proving how these functions relate should not be any more difficult. So this is all implemented inside of Devoid, which is a Coq plugin for Coq 8.8, and it's part of this Pumpkin Patch plugin suite, which you can find at this URL. Now, Devoid is an acronym, but I think we went easy on you this time, because this is the Pumpkin Patch acronym. The acronym of Devoid, its namesake, comes from these things called ornaments, which are at the heart of how Devoid works. So ornaments are what let us get between lists and vectors. The ornaments describe two inductive types that have the same inductive structure. So there's an ornament between a list and a vector, or between a list and a natural number, but there's no ornament between a list and a binary tree, because a tree has this extra inductive case. So ornaments were introduced by Conor McBride in roughly 2010, 2011. Since then, there's been a lot more work. But what this work has in common is that traditionally, ornaments are a programming mechanism. So this work asks the question, given a list and an ornament that describes the relationship between a list and a vector, how can I derive a vector from that? And how can I use that to port functions and proofs between these types? But we sort of flip this upside down. We search for ornaments. So we say, given two types that already exist, like a list and a vector, how can we automatically identify this ornament? How can we search for this, and then use the ornament to port functions and proofs between these types? And we focus on a particular kind of ornament called algebraic ornaments. And these ornaments have an additional property, besides just having the same inductive structure. And that property is that the new type is the old type indexed by a new index, which is determined fully and uniquely by a fold over the old type. So here, the vector is our new type. Old type is a list. Our new index has type nat, and this is determined by the length function of the list. So this describes our hello world example. It also describes many more examples, and you can find a lot of these inside of the Devoid repository. But for the sake of this talk, I'm going to focus mostly on this hello world example of lists and vectors, just because it's easier to understand. So let's take a look at actually using Devoid on this example. Devoid has two commands at its heart, find ornament and lift. So find ornament is what discovers the ornament, and then lift is what lifts functions and proofs along it. So find ornament, in particular, discovers two things, which I'll talk more about later, but it discovers this fold, like this length function, as well as an equivalence that describes how these types are related. So here this equivalence says that lists are equivalent to packed vectors. They're equivalent to a vector of length n for some n. Then lift is what gets functions and proofs across this. So it will take our zip function here to this zip VP function that's defined over these packed vectors. And this new function will have the same behavior as the original zip function. This zip VP function deliberately has the same behavior, but it's still not really taking advantage of the benefits of dependent types. It's not quite the zip V function that we saw earlier that rules out these inputs of different lengths. So if you'd like, we have a little bit of additional automation that will help you get all the way to a better type like zip V. And I'll talk about that later in the talk. But that's only the human workflow. So Devoid is also useful for hooking into other tools. So, Devoid discovers these equivalences automatically. So this means that we can use it to search for and prove equivalences that other tools can then port functions and proofs across as well. And in addition to this lift command works by a program transformation. So our new zip VP function is not defined by converting these packed vectors back to lists, calling zip, and then converting back. Instead, it's defined directly over vectors. And the result of this, our functions are fast and small, and our old zip function, and our proofs are also small, and our old zip function is actually obsolete. So, if we'd like to get rid of it, If we're evolving some kind of program and we want to evolve our proofs, then we can do that. So the first two of these, the search and optimization, we've done in our case study. So you can read more about this in the paper, but effectively we've hooked Avoid into this equivalences for free univalent parametricity framework, which is a more general framework for porting functions and proofs across equivalences. And as a result, of using Devoid, we were able to automatically discover and prove equivalences that the user would otherwise, have to write by hand. And for the class of types we support, we were able to, produce lifted functions that were up to hundreds of times faster and lifted proofs that were up to thousands of times smaller. So, this could be a useful optimization to hook into something like this. And in addition, this third step, evolution, is why we consider this tool a part of the Pumpkin Patch plugin suite. So Pumpkin Patch is a proof repair plugin suite, and we view this as a continuation of that work. So I mentioned these two commands, find ornament and lift. Now I'm going to go into more detail about these two commands, starting with find ornament. So find ornament, again, takes two types, like a list and a vector. Now it assumes there actually is an algebraic ornament between these types, and it makes a few other assumptions, which I talk about in the paper. Now from that, it discovers this equivalence that we saw earlier. So this equivalence is a pair of functions, here LTV and VTL, that get you back and forth, along with the fact that these two are mutual inverses. So if you send some list L along LTV, and then send it back along VTL, you'll get the original list, and this is called section. And then, the analogous property in the opposite direction is called retraction, and both of these hold. So in addition to this equivalence, Devoid also finds a fold, like this length function. And this fold is related to the equivalence in a particular way. So if you send list along LTV, and then you take the left projection of the result, this is the same as just calling the length function to begin with. And this property is called coherence. So this altogether is how algebraic ornaments are represented in Devoid, in equivalence along with a fold that's related to the equivalence in a particular way. So now let's take a look under the hood of actually calling find ornament on this example. So the first thing that find ornament does is it looks for the new index that's in the new type but not in the old type. So here it can do this just by looking at these two types. It just sees the nat. This is sometimes a little more complicated, and you can read about how we handle those cases in the paper. Once it's found that index, it then searches for the fold, like this length function. And it does this by looking at the types of the eliminators for lists and vectors. So this will take the same parameters, it will eliminate over lists, and then it will produce a natural number, because that's the type of the new index that we've discovered. In the base case, it will just return 0 because that's the index at the offset that we've discovered. And in the inductive case, it will just take the successor. And all of this will give us the length function. Once Devoid has found the length function, it can then search for these functions, LTV and VTL, that make up this equivalence. And I won't go into detail about this, so you can find more information about this in the paper. But just quickly looking at LTV, it's pretty similar to this length function because it's produced in a similar way, except that we produced a packed vector now instead of a natural number. To do that, we call the appropriate constructors of the packed vector. And in order to actually get the index of this vector, we call the fold, here the length function, that Devoid has already discovered. So this is how we find LTV, and VTL is similar. So by default, when you call find ornament, it just stops here. It just finds this length function and then LTV and VTL, and doesn't prove how they're related because the lift command doesn't actually need the proofs. It just needs that they hold. But because this is ITP, and we really like proofs, we've included two options in Devoid, which will actually spit out proofs in Coq of coherence, if you set proof coherence, and of section and retraction, if you set proof equivalence. There's a little bit of detail about how these work in the paper. You could also look at the code for this. It's only a few hundred lines of OCaml, so it's very simple. And it gives us a lot of power to hook this into other tools. So that's find ornament. Then once you've called find ornament, lift is what gets you along the equivalence that find ornament has discovered. In this example, getting us from zip to zip VP. Now I mentioned earlier that these have the same behavior, and what I mean by that is that if you were to call LTV on the result of calling zip on the two inputs, this would give you the same result as if you called this new zip VP function on LTV of each of the inputs. So that's what it means, for a function to be correct. Once you get to stating what it means for a theorem or proof to lift correctly, this is a little bit more difficult. We state this in terms of a relation from this equivalences for free work. And this relation essentially just says that lift is correct when the input and output of lift are equivalent up to transport along the equivalence that find ornament has discovered. So let's take a look under the hood of lift now, also using our hello world example with lists and vectors. So let's take a look at the constructors, because these showcase a few interesting points. So I'll show you how we get from this nil and cons to these packed nil v and cons v constructors over vectors. So for each of these, it starts off kind of similar. All it does is call this LTV function that Devoid has already discovered. Then it normalizes effectively the result, which gives you something that looks like this. Now, in the nil case, we're done because we have something that doesn't refer to lists in any way. We just have, for some length 0, the nil v has that length, and that's it. In the cons case, we're not quite done because we still have these references to LTV because, effectively, we're still assuming that L is a list. So Devoid has produced a body that type checks in the old environment where L was a list. But we want something that type checks in this new environment where L has been lifted along the equivalence to a packed vector. So what we do is we recursively lift this body again in this old environment where L was a list. And this uses the properties of an equivalence, this section of retraction properties, to eliminate LTV, and this will give us something that type checks in the new environment. So that's how we get our cons constructor, and these are our two constructors for packed vectors. Now, I won't go into too much detail about other functions, and you can read more about these in the paper. This is just for time constraints. But just one note about how we handle eliminators or induction principles, because this really showcases where ornaments shine. So we're able to lift eliminators directly. We're able to port our old eliminator, like listrect, to a new eliminator, like vectorrect. So if we had a function or proof that inducted over lists, we now get one that inducts directly over vectors. So again, this is where ornaments really shine. The reason that we're able to do this is because our inductive types have the same inductive structure. And as a consequence of this, we're able to produce functions that are small and functions that are fast, proofs that are small, and to get rid of this obsolete old function if we'd like. So this is really powerful. It's something we really get out of ornaments. Now, we have this algorithm that we've designed, and then we actually implemented this whole thing inside of Coq, and these things were sometimes in tension. So I talk a lot about all of the challenges that we encounter in scaling this to a real proof assistant inside of the paper, but I want to focus on just one for the sake of this talk briefly, and that's supporting fixed points. So the zip function that we saw at the beginning is a fixed point, and we don't actually lift fixed points directly. What we do is we lift eliminators instead. We lift applications of these induction principles. So we have this preprocess command, which is implemented by Nate Yazdani, which automatically translates certain fixed points and match statements to eliminators so that we can call lift normally. And this is just one challenge that we faced, but it's a particularly common one. So we've made this plugin available as a standalone plugin if you'd like to use it for your own purposes. So it's called Fix to Elim, and you can find it at this URL. Now we've seen the core functionality of Devoid. We've seen this find ornament and lift. But sort of deliberately, we still have this function that's no stronger than what we've started with. This function that doesn't really take advantage of the, the benefits of using dependent types. So let's keep going. To get from this to something like zip v, we start by using this onpack command. So this is something that we've also included in Devoid, and this is also implemented by Nate. And what this does is it gives you something over vectors that enforces some invariant. But it's not the prettiest invariant to look at. Eventually we want something maybe like zip v min, but we even have a little bit of artistic liberty because we could also choose something like zip v. We saw both of these earlier, and these are both true. Devoid can't choose which of these invariants to actually prove for you, and it can't prove it for you, but it can make that whole process a lot easier. And it does that by allowing you to prove it over lists, over unindexed types instead. So here we can prove this zip length invariant instead, which is the invariant that the lengths are the same. And then we call the same two commands, just lift and onpack. And this gives us an invariant over vectors. And then what we're able to do is define our zip v function by just rewriting by the lifted and onpacked invariant inside the lifted and unpacked function. And this gives us the type that we want. So now this is how we get from doing 3 different things at once to just doing 2 easy things. Now I mentioned earlier that once you start looking at proofs of how these functions relate, there's even an additional step. I want to talk briefly about this because this points to some really exciting work in progress. So I'm going to look at this zip width is zip function. Or zip width is zip theorem, which is from the same HS to Coq library. And this theorem relates this zip width function, which is like zip, but instead of putting them together into a pair, it uses a function to combine the 2 elements with the zip function that we just saw. This is a pretty easy proof over lists. Now, over vectors, it's not so straightforward. One of the challenging things here is that our zip and zip width functions before, our proof was just relating to functions. But now these 2 zip width v and zip v functions are defined over vectors, which means that they enforce invariants. So we now have to relate not only the functions, but also the proofs of the invariants. And this is a classic equality of equalities problem. And it still shows up right now when you're trying to get back a user-friendly type for your theorems. This is work in progress, but we think for the class of types that Devoid supports, we should be able to get this automatically without any axioms and without relying on properties of natural numbers or properties of the index, like the fact that NAT is an H set. You can see this issue for some of our current work on that. And we'd love your feedback because we think that maybe this is another place where ornaments really shine, where they really help us get something exciting and automate away a lot of pain. All of this is Devoid, something that gets us from this old reality of dealing with dependent types a little bit closer to what we really want by searching for these ornaments and then by using them to simplify this process of programming and proving with dependent types for a certain class of types. And it does so in a way that produces functions that are fast and proofs that are small, and it makes our old functions and proofs obsolete, so we can use it to evolve software as programs change over time. There's a lot more that you can read about this inside of the paper and inside of the repository. Many more examples. You can see the automation, case study, challenges, the algorithms, everything that we're currently working on. And of course, you can pull the tool and you can play with it, and we'd love your feedback. So please let us know what you think, and I can take questions.